So with simplifying radical expressions and multiplying rational exponents, we have to also look at simplifying radicals. We've talked about simplifying radicals with square roots. Now we're going to look at simplifying radicals with other roots and how we do that. So let's just look at this first example, something we've already seen before. The same process applies to all of these. So let's review that real quick. The square root of 50. If you don't know, there is a little 2 here on the index. So when we find the square root of 50, when we break down the square root of 50 or simplify it, we look for perfect square factors of 50, the largest perfect square factor of 50, and we break it up into that factor pair. So we're looking at 25 and 2 is how this would break up. The square root of 25 and the square root of 2, because 25 times 2 is 50, and 25 is the largest perfect square. Now we can evaluate the square root of 25. So this becomes 5 square root of 2, and that is our answer. That is simplified. So remember, we looked for perfect square factors of 50 because we're taking the square root. So when we apply that to cubed roots, like number 2, we want to look for perfect cube roots to see if we can simplify. So first we see 18 and 15. You kind of want to remember what your cube roots are up to at least 5. Or not your cube roots, your perfect cubes are up to 5. So we have 1, 8, 27, and then 3 times 3 times 3 is 27. 4 times 4 times 4 is 40. No, I wrote that like that. 48. And then, actually, I take that back. It's not 48. It's 64. And then we have 5 times 5 times 5, which is 125. Okay, so those are your perfect cubes. So if you can see 18 and 15, they don't have any of these as factors. So I'm going to multiply 15 and 18 because that is a property of radicals that I can do. So I'm going to get the cubed root of 18 times 15, which is 270. And now I see if there's any perfect cubed factors of 270. And one should jump out, and that is 27. So I'm going to break this up into the cubed root of 27 and the cubed root of 10. Now I can evaluate the cubed root of 27, that's 3. I can't evaluate the cubed root of 10, so it just stays like it is. So 3 times the cubed root of 10 is the simplified version of this example. All right, example number 3. I have the 6th root in example number 3. So I've got the 6th root of 8, the 6th root of 16, the 6th root of 2. Knowing your perfect sixths isn't something that you need to know. But you can write them down fairly quickly. I mean, 1 is always the first one. And then 2 to the 6th. Well, 2 to the 5th is 32. So 2 to the 6th is going to be 64. And then 3 to the 6th, I wouldn't even worry about that because that's a huge number. And unless you're dealing with huge numbers, you're never going to get there. So really, 1 and 64 are what you're going to be dealing with. So I'm not for sure. Let's see. There's no 64. Obviously, isn't a factor of 8 or 16. So because these have the same index, I can multiply the radicals. So I'm going to do the 6th root of 8 times 16, which is 128, over the 6th root of 2. Now again, because these are like radicals, or not like radicals, I'm sorry, because they have the same index, I can divide them. I can rewrite this as the 6th root of 128 over 2, which equals the 6th root of 64. And I just said that the 6th root of 64 was 2, or 2 to the 6th is 64, so the 6th root of 64 is 2. 2 times itself 6 times gives me 64. Just keep this in mind whenever you're breaking up radicals. We started simplifying radicals a long time ago with looking for perfect squares because we were taking square roots. So the process that continues is whatever root you're taking, you look for that perfect nth root. So if I'm taking the 6th root, I look for the perfect 6th. If I'm taking the 5th root, I look for perfect fifths. 3rd root, I look for cubes, and so on and so forth. The last thing we're going to mention, we're not going to do any examples, but I want you to think about this. Rationalizing the denominator. In the past, we've had 2 examples of rationalizing the denominator. We've had an example like 1 over square root of 2, or you just multiply by the square root of 2 over 2, effectively multiplying by 1, but you're getting that radical out of the denominator. So your answer here would be the square root of 2 over 2. That's the one way we've talked about. The other way we've talked about is multiplying by the conjugate. When you have 2 over 2 plus square root of 3, you multiply by the conjugate over itself. And you would get your answer. So what I want you to think about is, do these same rules apply when you have problems like down here in red, like 1 over the cube root of 3, or 2 over the 4th root of 2, or 6 over 1 minus the cube root of 7? Do these same things apply? And I want you to try and work these problems out yourself. I want you to try and simplify, try and rationalize the denominator for these 3 problems. And by rationalizing the denominator, I mean no radicals of any kind in the denominator. So give that a shot and come into class with your questions.